All right. Hello, everyone. My name is Sarah Albaraka, Strategic Content Editor at ASME, and welcome to today's webinar, Advanced Photopolymers, Accelerating Product Development, brought to you by our friends at Protolabs. All right, just confirming that my mic is working. All right. So once again, welcome to today's webinar, Advanced Photopolymers, Accelerating Product Development, brought to you by our friends at Protolabs. I will be the moderator for this event, but before we get started, let's get some simple housekeeping items out of the way first. So the console that you're looking at is completely customizable. Every window you currently see, from the slide window to the Q&A panel, can be moved, enlarged, or collapsed. So if you want to change the look and feel of your console, go right ahead. And if you have a question for our speakers, please enter it in the Q&A widget. We'll get to as many as we can during the live Q&A portion at the end. And if you need to leave early for any reason, don't worry, the presentation will be recorded and available for on-demand viewing starting tomorrow. Now let's get into today's topic. Advanced photopolymer capabilities powered by Protolabs and Axtra3D are transforming the way we approach design, prototyping, and manufacturing. This session will delve into the unique properties of advanced photopolymers and how they are leveraged to enhance product development processes and applications. Discover how businesses can achieve faster time to market with reduced costs and better product quality by integrating advanced photopolymers into their development cycles. The outcomes for today's webinar are for attendees to learn what advanced photopolymers are, key applications of advanced photopolymers, and an overview of Axtra3D technology. It is my pleasure now to introduce our speakers for today's program: Eric Utley, 3DP Applications Engineering Manager at Protolabs, and Rajiv Kulkarni, Chief Strategy and Marketing Officer at Axtra3D. Eric has more than 16 years of experience in rapid prototyping and additive manufacturing. His focus is on stereolithography, selective laser sintering, and direct metal laser sintering technologies, and he provides guidance to engineers on designing for manufacturability. Rajiv is a distinguished entrepreneur and executive with 3 decades of leadership experience in 3D printing, business strategy, innovation, and entrepreneurship. He leads all strategic initiatives and planning at Axtra3D, a global 3D printing OEM. Thank you both for joining us today. And Eric, I'm going to hand it over to you.
Sounds great. I'll get us started here. So first, we're just going to start with some introductions, just in case there are attendees here who haven't heard of our companies, Protolabs and Axtra3D. Just going to set the ground, get everyone up to speed as to what our place is in the 3D printing industry, and what led up to this collaboration, and kind of why we're excited to talk about this subject. Then we're going to go through the different materials one by one, and kind of speak to what they can be used for in the applications, and then follow up with the Q&A. So just quickly, who is Protolabs? And I'm going to be speaking from a very 3D printing centric point of view for this, given the topic. But in general, we're a custom parts manufacturer. I've been in the industry for 20 years, or more than 20 years. And I generally think of it as custom parts, historically very much in prototyping, rapid prototyping, but more and more recently, more into production space and in-use parts as well. And easily a decade back and more, we've been in production, but more and more it is moving that way, despite the name of the company. I'm out of Raleigh, North Carolina, which is our 3D printing lab, and we are the 3D printing division for the Americas for Protolabs. So if you order a 3D printed part from protolabs.com inside the United States, it would be made at that site. I have some pictures here of the 2 buildings. We're really just right next to one another on the street. Collectively together, it's about 200,000 square foot, purely focused on 3D printing, manufacturing, additive manufacturing. And we have over 120 3D printers here, and these are industrial 3D printers. We actually don't offer FDM out of our factory. So these are the high-end industrial level 3D printers that we offer to our technologies, offer to our customers. And of those, there's kind of 6 families of technologies for that. So really, as a 3D printing organization, we have I think arguably some of the most broad capability of anyone out there. And as I mentioned, we're not new to this. We've been in the 3D printing industry for over 2 decades. Deep roots in stereolithography. We were running some of the early commercially available stereolithography printers back in the day, and then more recently, we're now offering technologies like multi-jet fusion and direct metal laser sintering for metal parts. But we have a deep aptitude in the technology. And again, I'm trying to speak to the industry in general and what our place is in it, because we're not a machine manufacturer, we're not a material manufacturer, we're a parts provider or a service bureau. So, and this is really a key competency of ours, is you can upload a 3D CAD to our website, pick a material, and within about a minute or two get an orderable quote to produce that part, and we will give DFM, design for manufacturability, feedback on that part, and you can order it and get the part as fast as one day. Typical order, especially in this technology, you're looking at maybe about 3 business days from the typical order. So, if you're looking to buy the Lumia X1 from Axtra3D, I'm sure Rajiv will happily sell you one. But if you want to perhaps test drive the technology, or you have a more limited need for it, you can't justify investing in it and setting it up at your facility, we're able to make that technology available to the masses here, and you can upload and order these parts. And this is super common. I see it all the time. Companies are conflicted of should they invest in the technology or not. And we give a kind of a low or no risk way to get in and try these technologies and see if they make your life easier and allow you to focus on product development or whatever the core competencies are for that technology. And of the as I mentioned, we offer 6 different 3D printing technologies just inside of 3D printing. And sometimes I get asked the question, why so many technologies? And my response to that is typically, if there was a single best 3D printer, then that's all we would run. But in truth, all these different technologies, they're tools at the end of the day, used to fix a problem. And depending on what the problem is, you want to use the right tool for the job. And so, some of these printing technologies, they're cheaper than others. They print in different materials than others. Some are more accurate than others. And so, depending on the part needs and the project needs, you're really going to be looking at different technologies. And DLP-based technologies have been around a long time. We've offered DLP technologies for a few years now, and you can see the Axtra3D Lumia printer does kind of occupy a unique niche in this sort of landscape of 3D printing. So it offers a really unique solution that these other printing technologies can't offer. So I think a natural comparison is to traditional stereolithography, and you can see stereolithography's on this chart is up towards the top. This the furthest to the top. And despite being one of the first, if arguably the first 3D printing technology invented, it really still excels at very small feature resolution and tight tolerances and smooth finishes. So, as you can see here, typically a customer is asking for a trade show part, saying, I want this to look really good. I want it to feel really smooth. We would typically look at stereolithography, but the materials are limited because it's cured with a laser, and the photopolymers have traditionally just not been well suited for long-term use and are not that impact resistant and discolor with exposure to UV. So typically, if a customer is looking for an end-use part, a longer-term use part, we would typically advise against that technology. And then another interesting comparison is to SLS and MJF. They're kind of cousin technologies. They're very similar to one another. And if you're unfamiliar with those, they're powder sintering technologies. So you have a very fine plastic powder, and using heat, it's sintering those powders together, and you get excellent material properties. They're very impact resistant, but because of that powder sintering technology, the parts have a little bit of a powdery texture finish to them. They have, I describe it kind of like unpainted drywall. If you're ever at a hardware store, and can feel that, they have this kind of natural textured finish. And of those two, MJF has the finer feature resolution, but it's still at about a 0.5 millimeter. It's about the thinnest feature you can go. So again, there's this trade-off of the materials are more suitable for long-term use, but in turn, you're giving up tolerances, you're giving up surface finish, you're giving up the small feature resolution. And this is really where Axtra3D really is coming in with an excellent solution here, that you're able to really get the best of both worlds in that sense, that you get SLA level smooth finishes and small feature detail, but the material properties have advanced quite a bit since SLA has been around this time, and really kind of pushing the envelope and the level of the materials for this up to the point where they can be used in in-use applications and for longer term periods of time. And so that's all really exciting. And you'll see on our website, we call this we were trying to think of what's the most straightforward description of what this is, you could see we call it advanced photopolymers because it is still a photopolymer similar to traditional stereolithography in that sense. But we do genuinely feel this is a very solid advancement that occurs in this technology. That this has just been a typical or a long-standing limitation of photopolymers is the material properties. And so, and again, there are multiple DLP technologies out there. We've ran them before. There's really 3 reasons that we went with Axtra3D, and I'll let Rajiv go into more detail on that. But essentially, one major point is that it's an open system. And so this is a big change in general. Typically, the manufacturers of the 3D printers, they will limit the systems to just materials that they sell, and will limit it that way. And it's a great way for them to make money, but it also really stifles innovation on those technologies. That again, some of the stereolithography materials we run have been around for 2 decades plus and haven't advanced or changed in that time period. So this by having an open system, there's now a market for traditional manufacturers who, like, you can see these names like Henkel and Loctite, Arkema. These are very competent chemical engineering companies who are used to making production grade materials, and there's now a market for them to enter to offer production use materials for these 3D printers. And so that's all very exciting. And then I'll let Rajiv go into more detail on some of the aspects of their technology that enable them to get better feature resolution, and I'm sorry, it's more like a surface finish, and and I'm sorry, it gets better surface finish on the parts due to it's not just a DLP projector, it's bordering with a laser as well, and so you get really truly stereolithography level surface finish, which is really unique. Virtually every other DLP style printer has there's different people use different terms. Some people call it aliasing, which is a term from like 2D imaging. I tend to call it voxelation because it is essentially voxels. But what you can think of is it's very akin to Minecraft. If you look at Minecraft and you see everything's made with a little small block or brick, when you look at these parts up close, they have this sort of finish that's a relic of that DLP manufacturing process. So Axtra is really innovative here with their bordering laser and getting that stereolithography-like surface finish. And then there's some geometry limitations that come with DLP, particularly from the way it pulls parts up. I'll speak more to that later. But the short way of saying that is DLP printers typically struggle with really thick parts and have some geometry limitations that Axtra has a way around. So again, those three combined together feels like a really great advancement to the technology in general, and is really why we wanted to call it that, because it does feel like a very solid progression of the technology. And you know, again, we're now able to offer that to our customers. We launched it a few months ago, and just recently we quite literally doubled down on the technology. Our customers found the value in it and began ordering it, and our lead times went up. And so just very recently we added our second machine. We're looking to add more. So we have the capacity now to take on additional orders. You know, Rajiv will speak more to it, but they print very fast. So despite there being only 2 printers, they really have quite a lot of throughput for it. So, and I'll speak more to this later as well, that you know, we really can support quite a lot of capacity with these two printers, and can offer this technology to our customers. So I'll let Rajiv tell you more about how this technology works.
Thank you, Eric. You know, you mentioned an important point about the technology being unique. So as an introduction to Axtra3D, the company, let me touch upon first what really makes it unique. You know, our approach is grounded in 3 core areas. I'll bring it up right now. It's really, the intent was to deliver the highest quality parts with maximum flexibility on how you as the user adopts the technology. So the first cornerstone of really what we were trying to do is the high-speed SLA technology. This is where we combine 2 key innovations. One is the hybrid imaging, and second is the reliable layering. And I'll touch upon in the next few slides on how we combine these 2 together, but it enables the highest throughput without sacrificing quality. The second aspect of what we focus on is really our business models. And we have very flexible business models, like Eric mentioned, fully dialed solutions, but at the same time, we provide open access. And so you can choose what works best for your needs. You're not really restricted in any way. And that has been helping and building real great partnerships and relationships with us and our customers with their customers, I feel. And the third aspect that we really focused on was our material ecosystem. And what we have created for you by working closely with top resin partners is we made sure that you have access to the best materials for each of the applications that you would ever go after. There are no compromises required on that front, because if you need a specific material, then either we've already qualified it for you, or you can come back to us and we'll help you do that. So we're very open in that respect. And these 3 things is really the business model, the material ecosystem, and a technology that really removes all the issues and the concerns with traditional and conventional SLA and DLP is what really makes our offering very unique. So there are 5 things really which come into play when you print parts, right? It's accuracy, resolution, finish, part size, and throughput. From day one, our goal was very simple. We wanted to make sure that speed and quality aren't an either-or choice. You should be able to get the accuracy, the resolution, and the surface finish with a very high print throughput, and still have the ability to build large SLA-like parts without any compromise. Irrespective of your target application, we felt that you shouldn't have to make a trade-off between any of these 5 important characteristics of the process. And for example, not just be limited to lattice structures, right? You really want to build large, blocky, flat parts, then you should be able to do that. Our machine builds about 0.5 meter long parts, and they're 20 microns flat. So the intent was to make sure that all the trade-offs between SLA and DLP are eliminated through this technology that we offer. So here's really the crux of how we came about doing this, right? To expand on really the intent and the why. Let's step through quickly the pros and the cons of SLA and DLP just by itself. If you look at SLA, right? Conventional top-down SLA has always been the go-to technology for printing large, high-precision parts with great resolution and surface finish. But while it offers that, it also comes in with certain cons that really do not enable it to go into a high-end production, right? So there are slow recoating times, there are expensive vat fills for each machine that you have to do. The material changes are extremely long. And worst of all, I feel is you have really slow throughput because of the raster scan that the laser is doing. So for the accuracy, you really have to trade off throughput, and you have to trade off the flexibility in working with efficiently with different materials for different applications. If you move to the DLP or the projector side, really, I think the story flips. And the story flips in a way where you get the fast material change, you get the no recoating aspect of it, you get a really compact footprint of the machine, no vat fills, and you get the high print throughput. But every advantage of SLA, oh, I'm sorry, I have to clean that. Every advantage of SLA becomes sort of a disadvantage on this side. You lose on precision, just like Eric was describing. You lose on the precision, you lose on the accuracy, you lose on the resolution, just because now you have to work with a pixelated image. And then the layered effect shows up, and there's post-processing to be done. So when we looked at high-speed SLA, we said we would love to take all the advantages of SLA and the advantages of the projector-based systems and bring it into one system. And anything which remains behind, which typically is a WAD-based system with a projector on it, we feel was one of the worst combinations of doing a newer system. And the best and the ideal approach was to really get a laser and a DLP on the same system without a WAD and without recoating on it. So if you take all these advantages, you really get best of the both worlds, and you get no capability trade-offs, and which is why you can do surface finish accuracy, resolution, part size, as well as throughput at the same time, because you take the best of SLA for certain areas of the print, and you take the best of the projector for certain areas of the print and bring them together. So let's quickly look at how this happens, right? What are the two technologies that really enable this? So there are two technologies. One is an imaging technology, and the second is a layering technology. The HPS, which is hybrid photosynthesis, is our imaging technology where we get a laser and a DLP into the same curing system. And the layering technology is two-layer, which really, there's one aspect of it which is before the curing, and one other aspect of it which comes into play after the curing. But essentially what happens is you get a part which is about 0.5 meters in Z and about 10 by 6 in XY, quite efficiently, quite effectively. The system is designed for production, and the system is designed to be handled by robotics if you need to put it into a production environment. And it is a true end-use production system for end-use parts. So let's look at what HPS really is. Now, in this specific animation that you're seeing, if you look on the left-hand side, you will see that a single layer has been drawn by a laser, and it takes about 78 seconds for that laser to cure with conventional SLA, which just comes with a laser. Now, on the right-hand side, you see the laser and the DLP working simultaneously. And in our case, they work simultaneously, they work coaxially at the same time. It is not that a DLP follows the laser or the laser follows the DLP. They work simultaneously and coaxially to increase the throughput. The DLP is used for everything inside the part, and the laser is used for all the contours and the externals of the part, which means everything that you touch, feel, and see on the part is done by a laser, and everything inside is done really quick for the fast throughput advantage that we want to harness out of the system. Simple thought, if you talk to my engineers, they'll say it's absolutely not easy, but they were able to solve the problem. And here's the result. A layer that takes 78 seconds on an SLA generally takes about 4 seconds with our technology on the HPS. And so it's anywhere between a 10 to 20x productivity based on geometry, size, number of parts on a layer. But typically we are seeing about the same SLA quality part being built with HPS about 10 to 20 times faster without any initial wet fill and without any recoating required. And that truly increases the value and the advantage that you get out of the system. And tying it back, right, it's essentially getting an SLA quality part at DLP speed without the disadvantages of conventional laser-based SLA. The second aspect, which is the layer separation technology. Now let's look at moving to the projector-based systems, right? So now that we've covered the limitations of conventional SLA and we shift the focus to projector-based, fundamentally, there are two disadvantages on the way systems are today. One is there's a layer gap between the recently cured layer and the film, and there is no real good way to consistently maintain that gap to what is required. So if you need 100 microns, it's really never 100 microns. It's somewhere between 90 and 110, let's say, and you have to account through software on how to solve for that issue. The second is once the layer is cured, there is an issue. So let me open up the slide. Once the layer is cured, the issue is the fact that there is a peel-off force that happens, and there's a big hydrostatic force that gets generated between the layer and the film. And that really compromises the layer and the flatness of the layer and the quality of the layer. So these are two inherent limitations where the gaps are not consistent before curing, and it's difficult to peel off the layer after curing. And that has led to DLP products being limited in the sense that you can either build on the small parts or you can build on the lattice structures, or you have to deal with the compromised layer and do finishing on the part later. So the goal here was now to really solve this problem as well. So what came into play as we started to tackle this problem was true layer technology. And there are two aspects of true layer. One comes into play, which is we call true layer adaptive, is before curing. And another aspect of it that comes back after curing. And so how does it truly do it differently? So true layer adaptive adjusts the glass that is underneath the layer dynamically before it cures each layer, which means if we need 100 microns, it's exactly 100 microns. And because of that, we never have to overcure the layer because we know that the gap between the previously cured layer and the glass is exactly what's required. And as a result, there is no bleed out in XY because there's no overcuring required. And since there's no bleed out in XY, we get pristine sidewalls, we get extremely accurate dimensions, and we get the flatness because of the peel off that we do differently. As such, what Eric was mentioning is the part quality is extremely detailed, extremely accurate, high resolution, and quite different from what we get today from conventional systems. Now, if once the gap is adjusted, as we saw in the previous sort of slide, is there were vertical suppression forces that created hydrostatic forces. In our case, we came up with what we call as true layer separation. And true layer separation is instead of vertical separation, we separate the part laterally from the film. And what happens is this completely almost eliminates the hydrostatic forces, yielding a very pristine layer. It results in absolutely a mirror image of the glass that is underneath it, which is at a 20 micron spec. And you will see that even a 9x6 flat is within 20 microns because of the fact that we peel the layer in a sideways direction rather than in the vertical directions. We can build about half-meter parts, and through that half-meter dimension, whether it's 25 microns, 50 microns, 100 microns, 200 micron layers, we get the same exact result all the time. So the question is, yes, so we have these two technologies, and what are the resulting capabilities that are enabled by these technologies? So What you see here is a 9x6 mold insert. It's a ceramic mold insert that was printed, and you will see that the surface of the machine is within 20 microns flatness, which means this insert does not have to be machined anymore before it can be put into the mold press. And it's one of the most important aspects on the fact that you can simply print a ceramic mold insert. You wash it, you cure it in the oven for 30 minutes. You can do a heat cycle if you require to, but then it can directly go into the press mold, and based on the materials that you jet, you can jet anywhere from 30 to 3,000 parts out of this. So it's a great advantage just because TrueLayer does not introduce any hydrostatic forces, and we get pristine flat layers and details and accurate XY dimensions of parts that we print. Second, quite obvious is really the surface that you see here. When you see this surface, precise organic surfaces, which means there's no post-finishing required on this part. The section of the part you see on the left is what you typically get out of a DLP or a projector-based system. And the part that you see on the right is what HPS gives you, which means now you're not only benefiting from the fact that the throughput of the part is really high when you're printing it, but if you are doing organic shapes with jewelry or dental or any other applications, connectors perhaps, you never have to finish these parts because they are two-dimensional, and all these organic shapes and flat surfaces are very precise coming off the machine. Accuracy, of course, there are no pixelation effects, there are no tessellation effects. What you see on the right-hand side are extremely detailed features, and they're very accurate features. So if you're printing connectors, or you're printing, again, jewelry prints or micromolds or microfluidics, the details are extremely precise and accurate because all these edges are done by the laser, and the DLP is only used in areas where we need high throughput for the part. Resolution, once again, if you see the difference between the left and the right, because of pixelation and whatnot, on just pure DLP projector-based system, it's a hit and a miss based on where the position of that high resolution feature lies. In our case, these are done by the lasers, so they're never missed, they're accurate, and they are to spec almost in all cases. This one, it's trying to highlight exactly, this image is trying to highlight the fact that every layer, its edge, its boundary, and how it's placed on the previous layer is always precise. And it's precise because there are no hydrostatic forces acting on these layers. Reliable layering, in our view, gets you reliable results. Each layer is built under optimal repeatable conditions because of TrueLayer. It enables tight tolerances, fine details, consistent surfaces, and really delivers production-grade reliability. If you've never seen our parts, come to a trade show, ask us, sign up on our website, and we're happy to send you sample parts. And you will see that our parts are always precise. Every layer is exactly in the place it needs to be because of the combination of the laser with TrueLayer technology. And here's sort of the last advantage. DLP systems today print materials which are up to maybe 2,000 centipoise in viscosity. This printer, the HPS printer, prints materials up to 3,000 centipoise viscosity. We can do that again because of TrueLayer, where we don't have a hydrostatic force acting on the layer. And there are a few other technical innovations on how the layers are handled. But the fact remains that without any recoating and without any issues with the quality of the layer, we can truly handle materials between 25 to 30,000 centipoise quite effectively. Quickly touch upon the business models that we came on. There are two types of business models. One is extra solutions. And by extra solutions, we mean is we work with all the material providers, most of them in the industry, and we truly pre-validate print profiles for all their key materials. We then have application support for these materials, and we present you a very curated print material portfolio with keyword styles and a complete workflow established. The other aspect of it is we don't mark up our materials. It's at the same exact price that you would buy it from the supplier, but with us, it's fully dialed and fully tuned for our system. So you actually get a complete solution instead of having to do various things yourself and trying to figure it out. Now, if you have resins that you would like to experiment with on our machine, or you would like to bring in new resins, that's also okay. We let you build your own print profiles. In most cases, our customers come back to us and explain to us that they want to build with a new resin, and we go and basically qualify that resin for them on the printer, and then you can go and run that material on it. So whichever suits you as a business model that works for your needs is what you can pick. And it's a very sort of effective way to make sure that you can innovate at the same time, but also benefit from all the work that we've done to give you dialed solutions. And the last real aspect, the third aspect that we started off on the first slide was our ecosystem. We've partnered with Henkel, Arkema, Spectroplast, Nextent, Procedure, Keystone, Forward AM, and we've qualified most of their key materials for our systems. If there are materials that you need, if there are partners that you feel that you would want to work with, we're happy to consider those as well. And so it gives you sort of a best way to try out different things, try out different application. It gets you the best technology in your hands, but at the same time, it gets you complete exposure to any material that you might need for the application that you're targeting. We believe that you should be using the best material for the application that you have it at hand. And we feel that this trifecta of the technology, the business model, and the materials is what gets you there. And it's been one of the reasons why Protolabs has moved to a second machine. 25% of our customers now have moved to a second machine within a year because of this all coming together. This is kind of my last slide. I'll give it back to Eric. But here are some of the successful applications that our customers have done and are consistently executing on our machines. Whether it's mold inserts, whether it's ceramic parts, whether it's high temperature parts, whether it's real micro printing, anything is possible. We'll touch upon materials and applications in Eric's session again, and I'll come back to some of these exact materials. But all these applications that you're seeing go through this animation are what our customers are currently doing. Anywhere from 10,000 connectors a month to 12 different dental parts to true silicone to ceramic molds. Anything's possible. It's built for precision and it's powered by throughput. So I'll give it back to Eric at this point, and he'll go through all the different applications that Protolabs has been experimenting with, and then we'll touch upon certain new materials that we are focused on.
Yeah, so I'll go through the materials that we're currently offering at Protolabs, and you can order any of these on our website. And I'll start with the most generic one and kind of go to the more niche or specialty materials. So this is Henkel Loctite 3843. The resins are always a bit of a long name with some numbers and letters. So on our website, you'll see it's just called Tough Black. But we'll tie it back to that material, but just to give it a more common nomenclature. And this is just a very general purpose material. It's a very impact resistant, durable black plastic material. So you may say, what application can it be used for? It's almost easy to say, what can it not be used for? I'll speak more to this a bit later. It's naturally rapid prototyping, but again, this can be used in like end use parts as well. Something kind of note there is it does have some flexibility to it. You can feel it in the material naturally, and that 50% elongation is really quite big, and then about 5% at yield, and that kind of tells me like, and this can be a good thing, that if you have something like I always give the example of like a clip on the battery clip on the remote, the little door, you got the little flex piece that presses in and clips in. It's certainly flexible enough for like a little snap clip feature like that. and it'll wear in and get a little easier with repeated use from that. And to me, it's really most similar to like a molded polycarbonate. It's a little on the stiffer side, but it does have some flexibility to the material. So if you're still kind of thinking of it more at a rapid prototyping level, it can simulate polycarbonate quite well. And because of that smooth finish, because it's the hybrid process of SLA and DLP, it has that SL like surface finish. And then Axtra has some demo parts like that, and we're seeing this more commonly, really across 3D printing in general. It would be like these digital textures. So because of that surface finish, and because it doesn't have that aliasing, that pixelation, voxelation, whichever phrase you want, it really does create these like Voronoi patterns and really nice, interesting surface finishes you can get with the part. So you're able to really replicate that in an interesting way. Beyond that, and I'll speak more to this, it's kind of something that I think is a little slept on of, people, engineers, and will be thinking of, how can we use 3D printing to make our products better? And the knee-jerk reaction is always to that the end product is 3D printed, and for me that's typically not the way to go. It's really looking at the manufacturing process for that part and kind of asking if there was some custom tool used in this manufacturing process, does that make the product better and more accurate? The low-hanging fruit is usually jigs and fixtures, but it can be things like wire guides and spools and mandrels, things like this that really aid the manufacturing process. And I spoke to it earlier. Natural comparison is to MJF, the PA12 and MJF. And again, when I think of the PA12 and MJF, it's a black nylon. So I always think of the clip on a book bag is a black nylon, and you think of how pliable and flexible those clips are on it. So it's a little softer, a little less stiff than this material, and this one's a little bit more like a molded polycarbonate. So you can almost think almost more like a motorcycle helmet would be polycarbonate. And then of course the surface finish is vastly different. The surface finish and the small feature detail is much better on the Axtra, and I'd say in particular anything with negative space, critical negative space. So you think like slots and holes, internal cavities that are important to the function of the part. That's something that Axtra is just going to excel at much better than multi-jet fusion. And when we're talking about photopolymers, UV resistance always comes up, especially if you're talking about using it for long-term use. And it's something that I think that we kind of hold ourselves to a really high threshold. I thought about this the other day. I was replacing the antenna on the top of my car. That's maybe 10, 15 years old. And it just disintegrated in my hand as I was unscrewing it. And I was like, well, here we go. This is a production injection molded part that undoubtedly had UV inhibitors, and it only made it about a decade out in the sun for that. So I think it's worth kind of saying, like, when we say, is it UV resistant? It's like compared to what? And you can see here, this is fairly typical, but they'll be exposed to UV and you'll get some drop in the elongation. But then there's essentially diminishing returns. It sort of levels out. So if you can kind of design the part with some safety factor in there, then in theory the part could have several years of life out there. And because of the black color, typically that's the first thing to go is the color on these parts. So with the black color, it can really be in some applications where it's exposed to UV. The heat deflection temperature is reasonably high. I think of this as like a hot car in August, like now. Basically, it's kind of the top temperatures that you would want to see with that. If you were seeing higher temperatures than that, then we would err more towards the next material I'm going to talk about. And it does have some resistance to like common chemicals, like waters and oils. It holds up just fine. And then just some chemicals that particularly alcohols, acetone, it will degrade the material, but waters and oils and some other chemicals, it does have some resistance to. And one thing that we've adopted here is Cerakote, and these go together extremely well. So this is a part printed on an Axtra printer, and then it was lightly sanded. I will say that, and then we sprayed it with a Cerakote, which is a ceramic filled coating that came out of primarily the firearm industry. So you imagine these things are seeing a lot of wear and tear and heat and gun oil, and then hold up for a very long time. So again, looking at long-term production use parts, end use parts, this is if you are concerned about UV and the chemicals the parts exposed to, this is an excellent kind of way to address that. Would be Cerakote, and this is something that we do offer, and you can request on the quote. I think so. So we have some major advancements with the tech, right? It prints very fast, and the material properties are much better than typical past photopolymers. And those two together really raise the question of, is this really suitable for production? This is a race I set up between Axtra3D and injection molding, and this is unique because as a company we excel in low volume injection molding. So these numbers are, we're competing against molding that's catered to low volume. And so one part in here, that's like an actual game dice to give you a sense of scale. So, and it's just meant to represent something simple that's thick with a lot of material. And so it can be molded. So at 500 copy, up to 500 copies, Axtra is more competitive for that part. And the same with that other smaller part. So it's a little bit bigger, it's less material, and because you're trading off there, it's less material, but it's larger. I'll speak more to that. Then that one comes out about 500. And then this one part is an injection moldable part. It's about 7 to 8 inches in size. So now you're getting up a little bit larger, and now that crossover drops down to about 100. And so the main takeaways I want you to take from this are size and complexity. Size and complexity. That the larger a part is, the less scalable it is in 3D printing. That 3D printing in general, including the Axtra3D printer, is sensitive to scaling, and then also complexity. That these are very simple parts here, but as you start adding complexity to these parts, adding features, 3D printing is going to get much more viable in any sort of application where you're adding complexity to the design. That gains you functionality. So think like heat exchangers or extruders, and all number of different applications like that, or mass customization, personalization. Anytime that complexity increases the value of the part, that's when it can really take off. And as Rajiv said, if it's a complex small part, it can easily be in the tens of thousands of copies where it's suitable. And then 3D printing has historically lived. This is just the typical product development life cycle. 3D printing's really historically lived on the front end of this, before the little blue tab there. But again, with the advancements in the material and then the speed and the quantity, really starting to see it through that curve. So this could be an excellent solution for end of life parts where it just doesn't make sense to fire up a molding tool again anymore for a part. And then also it's just a natural trend that's happening, that you may have a one size fits all, or you may have a small, medium, large, or you can turn that dial all the way to the other end and have a completely personalized product for each individual. And so 3D printing kind of gives you a little bit of an off ramp here. So you may have a product out there that's made in a couple thousands a year, and it's like, well, there's this market over here that's interesting, where we have some people who would be willing to pay 2 or 3x the price, but it has to be custom, it has to be personalized. And then so this gives a solution to give personalized products for that. Sorry, I don't know if I was flipping through the slides properly. Here we go. Here's the ceramic filled material. So this is a very stiff, high temp material. And really it's meant for high heat applications. And I'll move a little faster here. We're getting close on time. But it's 65 ceramic filled. So it's not a true ceramic. It's not going to see several hundred degrees Celsius or 1,000 degrees Celsius, but it can handle, as you can see there, like 280 degrees Celsius. So very high temperatures. And the moon here is a great example of what we were talking about, that one of our engineers brought this to me and said, hey, we made this on one of the DLP printers we're evaluating. And it was a head scratcher because it's a big, thick part with a lot of small detail. And that's just something that a traditional DLP printer would really struggle with. So it was really interesting seeing that. There is a thermal cure that can be done on the material, but it's really not needed. It only raises the heat deflection temperature a couple degrees. But it's really interesting that you can get such a high heat deflection temperature without having any kind of post-process to that material. It's really used in any application where it's going to see elevated temperatures. And where you really need that low coefficient of thermal expansion. So you think like laser guides, where the whole system's heating up and you don't want the system to expand and push your lasers out of alignment, or manufacturing processes that see heat through that. So we see things like wire forming mandrels, tools that guide fiber optic cable, and then the injection molding tools as well that Rajiv mentioned. Some of our customers have on-site molding capability, and we'll print mold inserts and we'll see it. So again, it's seeing those high heat applications. Wind tunnel testing is very common. A lot of those I see with electroplating, which I'll mention later, which is another secondary process. And again, because this material can see such high heat, that it can be autoclaved, which is interesting because most photopolymers have to be gamma sterilized. Again, I like just including some post-finishing processes. So this is electroplating. We can offer electroplating on the parts. It puts a copper nickel coating on the parts, and it does a great job of increasing the wear resistance on the parts in particular, and the impact resistance. So you think of, take a ceramic plate, drop it on the ground, it's going to shatter. This does a great job of really increasing the impact resistance of that. And then real practical application is in waveguides. Usually those would have to be made in DMLS possibly, but you can do them usually cheaper in this process by printing in this ceramic filled material and then plating it. And it's very stiff and light. So we've seen, for example, like racing and drone applications, where you want a part and you want some increased strength, but don't necessarily want to invest in like a printed metal part, for example. And then big applications, like, again, this is what I like is the manufacturing tools. We've seen applications where you have like a smooth shape like this and maybe dip it in latex or like a silicone and come out and for like manufacturing gloves and things like that. So again, not the glove itself isn't 3D printed, but the tool used to make the glove is 3D printed, which is a great application of using 3D printing in manufacturing. And the last most niche material is a flame retardant material. So it's a Arkema FR512. This is a very stiff and fairly inflexible material. It has a very tiny bit of flexibility. But you're primarily going to see it in electrical connectors and data transmission. So anything that you would want to mitigate the risk of a fire starting. A lot of these parts are in very remote places, underwater or in space or on an aircraft. Something that you don't want a fire to start to begin with, and then it's also hard to address the fire. So we have a solution for that, and we're right up at time, but I'll hand it back here to Rajiv.
Yeah, just have one slide. We have 4 other sort of material applications in focus. We offer true silicone here, and this silicone is where the entire backbone of this material is silicone. There's no urethane or acrylate in the material after the part's printed and dried off. Really medical devices, skin touch, and industrial components. 50 Shore hardness. It's been a very, very useful material in many applications. ESD, of course, for connectors and anything that is closer to electronics from Loctite. We have the 1100 from Forward AM that's really useful for elastomer molds, so shoe sole molds and other molds that where you need rubber-like parts. It's been very useful and customers have been using it. And then the last one is the AMB 300, which gives you about 300 HTT for micro molds, really high HTT and excellent in very small parts, precise parts which require high temperature. So these are materials that are also available. I don't think Protolabs has used them or applied them as yet. They are in the process of experimentation of these to find the right applications, but there are other customers who are using it. And I'll stop there, and we are happy to take question and answer, I think, at this point.
All right. Well, thank you both for that informative presentation. And yes, we do have quite a few questions here. So let's see how many we can get to in our 5 minutes remaining. So the first one is mechanical strength of SLA parts with regards to the HPS DLP modeled as as printed strength or post-cure strength.
On the spec sheets, it's post-cured strength, actually.
Okay. The next question has multiple parts. I'll start with the first part. What measures are employed with the HPS process to ensure precision at such a higher throughput than SLA? And does laser intensity pose a risk to the polymers such that it can deteriorate the resins?
No, so the DLP as well as the laser are 4 or 5 nanometers. They're at the same wavelength. They work simultaneously, and the curing is no different than perhaps what happens on a conventional DLP and a laser system, just that it happens simultaneously here. And as such, you get parts that are very similar, but just they're very accurate, they're very fast. But the other risks that you mentioned are not real in this case.
Okay. The second part of that, are you able to employ SLA resins, and what fundamental differences like branching, polymer structure, etc., exist between them that allow such fast reactions?
So our system is designed for the 405. We've also tried the 385 materials from SLA. They work. The throughput is slow, of course, because the wavelength for the light is not designed for 385, but we have developed print process styles for certain customers where we've made 385 nanometers available. Just the throughputs are slightly slower than what you would get if it was a 405. So when we work with our partners, we typically have them create and ask them for 405 wavelength materials, I think.
Okay. This next one maybe is a quick clarification. Was it up to 3,000 or 30,000 CPS?
We can print up to 30,000 CPS viscosity resins, yes.
All right. Next question. Do you have any resins that are UL Blue Card certified for flammability, HB, VO, etc.?
I think Eric just covered that, I feel.
Yeah, it was interesting. I'm still meaning to reach out to Arkema on that, but that FR512 material, if it doesn't have a blue card, I would expect them to have it at some point, because that does kind of speak to its key application. But I would look at the FR512.
Okay. And next, how good is this equipment at printing fully see-through transparent parts?
Yes, so we have clear materials and we can print those. Of course, if you polish those, they will be much more clear, but we have clear materials and we can print clear materials.
Okay, and how does the surface strength compare to bulk strength of parts produced by, I think this is supposed to say Axtra, for example, or scratch resistance, etc.?
So here's what I'll say is there are certain materials developed by these partners which are scratch resistant materials, but typically these parts will behave just like any other SLA part in terms of scratch resistance, unless the formulation has been designed to be scratch resistant. So there's no real difference there, I think. What have you seen, Eric? If you want to add anything, I don't know.
Sure, go
Yeah,
ahead.
yeah, I interpret that as, you know, is there any difference between like the DLP cured and the laser etching? And we haven't seen anything
No, it's
definitively
very
on that.
similar. Yes,
Yeah.
correct.
All right, we're up on time here, but maybe squeeze in one last one. Have regulating organizations like ASME started providing material specifications for 3D printed materials?
I think so. Yes.
They're moving that direction. It's funny. I'm primarily on the metals side, and they're moving towards that direction. And the polymers tend to lag behind it. So it's certainly moving that direction, especially with these like more production grade materials. But there's definitely work still for them to get better regulations in place around that and standardization.
Okay, well, that is about all the time that we have, but I would like to thank you all for joining us. We hope it was valuable to you, and a special thanks to Eric and Rajiv for their time and expert insights. Also, thank you to our sponsor, Protolabs, for their support. So if you missed any part of this presentation, it'll be archived shortly so you can view it again or refer someone else to it. Thanks again, guys. Have a great afternoon.